Buddy, today we're going to quickly, and I mean very quickly, solve this problem expeditiously in an extremely efficient, evident, intelligent manner. This matter will be solved in an intelligent manner. Okay, 2948 make lexicographically smallest array by swapping elements. Doesn't that sound fancy? Okay, so you're given a 0 indexed array of positive integers nums and a positive integer limit. All right, in one operation, you can choose any two indices, I and j, and swap them. So I can swap nums of I with nums of j. Whoop! If nums of I minus nums of j is less than or equal to limit. Okay, so what that basically means is not the indices themselves, right? So it's not like the distance between indices, but the values at the indices will determine whether or not things can be swapped with each other. Okay, return the lexicographically smallest array that can be obtained by performing the operation any number of times. Okay, an array A is lexicographically smaller than an array B if in the first position. Okay, so an array is lexicographically smaller if you know it's like a smaller number when you look at it as a number. Okay, that's the best way I can think of it here, right? But you know the idea is here like 1, 5, 3, 9, 8. Well, 1 and 1 are the same, so they're equal. 5 and 3, well, 3 is smaller than 5, so it's lexicographically smaller, right? So you just look at each number going through the array, and whichever one is smaller in that position, right, starting from the left, is going to be the lexicographically smaller array. I hope that kind of makes sense to you already. It's a pretty fundamental concept, right? 176, well, 167 is less than 176, right? Because even though they're the same here, the 6 and the 7, they're different. Okay. And then this one's already in order. So maybe we'll do this one just to start. Okay, so in this example, we have 1, 5, 3, 9, 8. 3, 9, 8. Okay, so the limit being 2, what that basically means is it confines what can be switched with what, right? 1 and 5 are too far from each other to be switched with each other, right? Because 1 and 5, how far away are they from each other? Well, they're 4 away, right? 5 minus 1 is 4, and the limit has to be less than 2, okay? But 1 and 3 could go together, right? 1 and 3 could be switched. All right, and 9 and 8 can be switched. And, well, also 5 and 3 can be switched, okay? Now, the resulting answer, and this is a perfect example because it illustrates kind of the only observation you really have to make in this problem. The answer is 1, 3, 5, 8, 9. Now, you might look at this and say, well, the 1 and the 5, well, no, actually it didn't. So hold that for a moment, right? But we notice that, okay, we can switch these guys together because they're the same distance, so they get switched here. And we can switch these guys together, so they get switched here. So this isn't really the best example, and I apologize for that. So let's look at another example here really quick. Okay, we got 1, 7, 6, 18, 2, 1. Okay, we got 1, 7, 6, 18, 2, and 1. Now we play this game again with who can switch with who. Okay, so this 1 is not going to be, it's going to be highlighted. All right, so this 1 can switch with this 2 and this 1 because our limit is 3. This 7 and 6 can switch with each other. And this 18 really can't switch with anything. So if I wanted to make this work, well, the fact that there's more than 2, we can always switch around to make this work, right? Like I could switch this 2 with this 1, right? So I get 1, 2. Switch this 6 and this 7. Now I'm stuck with this 18, and then you see the answer is 1, 6, 7, 18, 1, 2. Okay, can we get an even better answer here, please? Something, give me something here. So none of these examples are good. I thought there was a good one, but I guess my memory has mistaken me. And that's the weird thing about these problems sometimes, right? Because the proof is in the pudding, right? The answer is really revealing. It really reveals itself, but you need a case which shows that to be the you need to make that observation, and if they don't give you an example that gives you the opportunity to make that observation, maybe you need to make one yourself, okay? Well, let's make 2 examples and think about kind of what the implications would be if that was the situation, okay? So first one, let's have 5, 3, 5, 4, 3, all right? And let's say that our limit is, I don't know, 2, okay? If our limit is 2, then that means that everybody can swap with everybody, right? 5 is less than 2 away from 4. 5 is less than 2 away from 3. 3 is less than 2 or 4. They're all within the range, right? Now, since there's 3 of them, we can make any limit any number of times. So we can really... Well, let's say this was a 4, 5, 3. Okay. All right, because I'm really trying to show you a case where it doesn't really matter that there's more than 2 things in a group, right? There's always a way to kind of flip it around and make it work. And what I mean by that is, okay, if we have 3, 5, 4, where I could switch, 3 with 4, and then I could switch 5 with 4. So the point here, right, is that even though I have more than 2, it doesn't really matter how many I have, and I'm not going to prove it, right? But it doesn't matter how many I have. If they're all within a range together, right? If they're all scrunched together, I can sort them, right? There's some way of flipping around and taking things. I don't just have to switch, 2 elements like this. I can switch them like this, then move these 2 over here, and these over here, and these over here, right? I can flip, mix and match, right? Any system of elements that are connected like this, I can sort them no matter what, okay? And even further than that, what if the difference here was 1? Okay, so let's say the same problem here, but the distance is 1. Well, now we have, a different situation because, 5 and 3 can't directly switch with each other, right? 3 and 4 can, and 4 and 5 can, okay? But what you'll notice is it doesn't really change anything, right? Because, all I have to do is switch this guy here, and then that'll be 5 here, but then I can just switch 5 with 4 here. Okay, so even though 3 and 5 can't swap with each other, right, I can always make this work because 4 can switch with 3 and 4 can switch with 5. So 4 kind of acts like a middleman here. Okay, and so what that really means, right, is if I had a situation like this, right, let's say I had 6, 5, 4, 3, 2, 1, right, and our limit was 1. I can always make this work. Always, because I can move the 1. I can't switch the 1 with the, I can't switch the 1 with anything but the 2, right? So how would, now I'm starting to wonder, can I actually make this work? Right, so I can't, so how would I make this work, right? This is kind of the most extreme example. So if I can show it, at least prove it to myself here, that I can sort this system even though they're not all connected, that would prove something to me. All right, well, I could switch, I don't know exactly how you would do it, actually. So I think you'd have to really slowly go through. So maybe if I switched the 2 and the 1, or no, I should probably get the 2 over. Right, I need to find a way. That's so hard, man. Okay, so let's switch the 5 and the 6. 4, 3, 2, 1. Kind of like a weird puzzle here. Oh, so I could do that all the way through, right? Watch this. Just to show you how this works, right? And then I could switch, because it doesn't matter how many times I do this, right? This is just trying to get the minimum. It doesn't matter how inefficient you switch things to make this work. So 5 and the 6, and maybe I'll switch the 4 and the 5. And then I can switch the 3 with the 4. Then I can switch the 3 with the 2. Then I can switch the 1 and the 2. Right, this is the most extreme example, right? It's the smallest limit, but everything's just connected by 1, and I can still move the 1 all the way over, right? Because as long as 1 is connected to something and that something's connected to something else, well, I can move that something in the middle to that something else and then shift me in at the end, right? That's what I did here, right? I'm trying to get 1 over here, so then I need to get 2 over here. When I get 2 over here, I need to get 3 over here. To get 3 or 4, right? So it kind of recursively goes down the stack. And I can keep doing this game, right? Now I can switch 6 with 5. And I won't do the whole thing, but just to get the 2 in the right spot so you can see this work. And voila, just like that, now I got, right? So the world is really my oyster here, right? I can go down this, I can play this game as long as it takes, right? So the point really is here is, well, I don't need to consider, like, as long as they're grouped together, right? As long as they're connected, I can sort them, right? So I don't need to really concern myself with the fact where, you know, they're not directly connected. As long as they are connected, I can sort them. The only time I can't sort them is if there's a jump between them that's too great, right? So when I look at this problem again in a different light, right, when I look at this problem again in a different light, I could say, well, I'll start painting things that are together. Like 1 is with 3 and with 5. These are all together, actually, right? So I could sort this whole system to get this here. 9 and 8 are together, so I can sort this whole system, get these here. And you'll notice that they're two different groups, right? Because 5 doesn't connect to 8. 5 can't reach over to 8 and make it one group. Okay, let's look at this problem again under a different light. So 1, 2, and 1 are all in a group together because the distance here was 2, right? Or there's 3, doesn't matter, right? 1 and 2 and 1, they're all in the same group, right? This 1, 2, and 1. And that's in the same group as before, the same kind of idea. And so are the 7 and 6, and the 7 can't go in because the 7 can't reach this 18. All right? Now let's see if I can get even a better example here that'll really kind of show this approach in detail. So let's say we had 18, 19, 4, 3, 2, or I don't know, 1, 2. All right, so let's say we had this example, and then again, the simplest limit would be just 1. Okay, so here, well, again, remember, I'm saying now it's about groups because it doesn't really matter, right? We saw here, right? It didn't really matter if the distance was 1. As long as they were all in the same group, I can, you know, mix and match and make this work, even if it's super inefficient way of doing it, right? So here you'll notice, well, there's kind of two groups, right? 1 is in a group with 2, right? But also 2 is in a group with 3, so that group gets extended to 3, which also gets extended to 4. And then 4 is not in a group with 18 because the distance is too far away. So you notice the natural way that I'm doing this, where I'm starting with the smallest thing and trying to figure out, like, okay, who's in a group together? And as soon as I reach a point, right, there's this point right here where, you know, from here to here, it's good, so I make another group. From here to here, it's good, so I make another group. From here to here, it's good. I'm not making another group. I make it in the same group. But to get from 4 to 18 is too much of a jump, so they'll never be in a group together, so I can never sort them together. And let's make this actually 19, 18. And just for the sake of trying to keep this at least a little bit consistent. But then 18 and 19 are in a group, right? Because now from 18... I could say, yeah, 18 are in a group together, and 19 gets extended into that group. Okay. Very sloppy work here, Ben. Good job. All right. So what does that mean in terms of what I can do? Well, I can sort kind of these two systems independently, right? I can take this 1, 2, 3, 4, and I can kind of paint over because I know that I can sort that system and make it work. It might not be, I don't know the individual swaps I'm going to have to do to make this work, but I know for sure that if I have a system that's connected like this, even though 1 and 4 aren't directly connected because the limit's only 1, 1's connected to 4 through 2, which is connected to 3 to 4, right? But somehow, some way, I can take this and make it work. So I can really just repaint the system, right? I can say, okay, this will be 1, 2, 3, 4. And then there's nothing I can do about these 18 and 19. Those have to be treated separately. They're in their own group, so they'll get treated 18, 19. Okay, so how do we make this work? Okay, the way that this is going to work, basically, is, you notice, we know when our exchange point is, right? When we find a new group, when we encounter a situation like this, where it jumps more than the limit. When it jumps more than the limit, then they can't be put together and there's a new group that's starting. Okay, so in order to make this work, what we'll end up doing, right, is we'll end up moving all this up because I really want a good screenshot here. Okay, what we'll do to make this work is basically, well, we're going to go through the indexes, and then every time we find a situation where we kind of pass that limit and we're not connected anymore, we're going to kind of start the system over again and find a new group until we find a group in that limit size, and then go on. What am I saying? I don't know. So basically what we'll do is we'll create a res array. This is what we're going to return. That's the size of the system. So we're going to use this problem again. So we'll start it all with zeros or nulls. It doesn't really matter. Then what we'll do is we'll take this array and we'll sort the indices. And what I mean by that is we're going to find the indices that are the smallest going forward, okay? So I'm going to kind of reference this as pointers because it looks cool, but it's not really, you know, what's going on here. So let's say 19, 18, all right? So what we'll do is we'll have pointers instead of, so we'll have this one pointer. The next element points to 2. The next element points to 3. The next element points to 4. The next element points to 18. Next element points to 19. Terrible idea this was because it's really hard to see. But okay, whatever. So what we basically do is we just, you know, we try to find all the arrays that we can find, right? So we know our first group will be at left. And then maybe we'll try to find the groups that make this work, right? So what we do is we ask this question. We say, okay, is the current element we're looking at right greater than the limit of the previous element at left? And we say, no, it's not greater than that distance, so then these two are a part of the same group. Okay? And then we shift over R. We play that game again. So we go up this link and we say, okay, is this element at R, right, going up this link, greater than the limit at the previous element? The previous element would be here, up this link, 3 greater than 2. No, so they're part of the same system. Then I increase R. Then I ask the same game. Is this R greater than the previous thing? Greater than the limit? Is 4 greater than 3? No. So they're part of the same group. Then I increase R again. And I say, okay, is R greater than the previous? Is the difference between my current R and the previous element greater than the limit? So I look at my element. Then I look at, I'm going to put this up so we don't keep. Then I look at my previous element and I say, okay, my current element's 18. My previous element is 4. So that distance is greater than limit. So then these things are a part of a different group, right? They can't be grouped together because the distance of them is greater than the limit. So I can't connect them and then try to, you know, play this crazy game that we played up here in order to swap things in. So this becomes a new group. Okay. Then I increase R again. And I just ask that question again, right? So I say, okay, is 19 minus the previous element 18 greater than limit? No, so they're part of the same group, right? Now we have our groups, and then we just have to paint over, right? So I say, okay, I have my group 4, 3, 1, 2. I'm going to go ahead and sort that, I guess. So it'll be 1, 2, 3, 4. And then I'm going to put it over all the members in the group in order, right? So my first element's here. So I'll put my 1. I guess I'm trying to think about how this is going to, how you can functionally see this work, right? Because these are really indexes. So their values, right, are, because they're not well, they're kind of like pointers, but they're values of the array, right? They're indices of the array, right? And the pointers are just indices of memory. Whoa. Well, there could be indices. Well, they're addresses, which are indices, but it doesn't matter. Okay, so this would be, what is this? These things all point. So this points at 0, 1, 2, 3. This points at 4. This points at 5. This points at 1. This points at 2. This points at 3. This is not a 1, 2. This is a 0. Okay, so basically how this works, right, is we have our first group here, right, which is 1, 2, 3, 4, and it goes into indices 3, 2, 4, and 5. So we have 1, 2, 3, 4, and it goes into the indices 3, 2, 4, 5. Sorted, that would be 2. Wait. No, not 2, 3, 4, 5. Did I get so confused? Okay. These were the ones that were together. Right, so the indices would be 4, 5, 1, 0. Oh, I'm sorry if this makes no sense. 4, 5, 1, 0. Sorted, that would be 0, 1, 4, 5. So then I replace that in the array, right? So 0 becomes 1. 1 becomes 4. Wait, 1 becomes 2. 4 becomes 3. And 4 becomes 5. All right, and then the next group are these two at indices 1 and 0. No, wait. Dude. The next are these two at 3 and 2. So then 2 becomes 18 and 3 becomes 19. And wouldn't you look at that? That's the answer, right? So maybe I'll walk through this again with these pointers and you'll see just one quick run of it again because I kind of confused myself and probably confused you with how this is supposed to work. So you can kind of see more so how the code will do it for that matter, right? I'm going to leave the little things there. So as we look at our left and right, we say, okay, left, right, are they left and right? 1 and 2, are they less than the difference? Yes. Left, right, 3 and 2, are they less than the difference? Yes. 4, 3, 4, 3, are they less than the difference? Yes. 3, 3. What's at 3? At 3 is 18, and the previous element was 0, which is 4. 18 minus 4 is not less than the limit. So then we're in a new group. So that means from L all the way up to this point is a group, okay? So we get this group here, and then we just basically sort it with the elements and the values, right? So our values sorted are 1, 2, 3, 4, and our indices sorted are 0, 1, 4, 5. So that means at 0, I put 1, and at 1, I put 2, and at 0, 1, 2, 3, at 4, I put 3, and at 5, I put 4. Right, so that means I get a new group, and that means I should probably move my left pointer over here and continue playing this game. And I look at R and I say, okay, are these in the same group? Yes. Are these in the same group? Yes. So then I have one other group here. And then I just play the same, silly game. So I look at the elements that are at 3 and 2. So at 3 and 2, there's 18 and 19. So 19, 18. So sort of that'd be 18, 19. And our indices sort of would be 2 and 3. And then I just paint 2, 18. Paint 2, 18. And I paint 19. This 3, 19. Okay. Hopefully that makes a little bit of sense. A little bit confusing because we're using this pointer solution. But, that's essentially what we're doing here. All right. What a terrible explanation. I swear I'm a good engineer. I swear. All right. So let's go ahead and actually write the corresponding code now. This is where it gets a little bit tricky because it's kind of this weird situation here to try to make this work. All right. So we got to find these kind of pointers first, right? And then start left pointing through to try to figure out, where things happen. Now, I hate this guy, dude. This guy, he's got to go. I'm sorry, guys. He's just this freaking turkey staring at me. I don't accept it. I don't respect it. And I don't appreciate it. So, see that? You get a small, he tries to hide from you. So usually you're in an inner div. So if you go out, look at how complex you're gone. Be gone. How do I be gone with this elements? Okay. Watch it not work now. Somehow embedded in that is something that relates to the submit button or something. Wouldn't that be hilarious? Okay, so we'll first create this res array, right? We'll say 0 times length of nums. Now the first thing I'm doing is I'm actually going to extend nums with an infinite thing, with infinity. That way we can kind of push to the end, right? Because if you notice, in what I just showed you in the note, right? When it got to the end, there was no real establishment of the right side of that kind of set. And what I mean by that, quickly, right, is when you look at this example here, right? When you look at the situation here, you'll notice that, I drew this line where I knew when I was in the situation because I compared 18 to 4 and I said, okay, I drew this line now here because I compared 18 to 4. But when I get to the end, there's really nothing to compare this 19 to know that it's the last element, and I can draw another line and then sort the set and then apply, right? So if I add an infinite to the end, I won't add the infinite to my solution, but then I'll have something to always compare this last element to create that line and then do that check, right? So it's just a little trick to kind of make your solution a little bit simpler, but of course it's not simpler because people are going to see this thing and be like, why the heck are you adding flow infinity to the end, right? So it is and it isn't. It's less readable in one regard, but also simpler in another. So, you know, there are no perfect solutions. There are only compromises. Okay. So what we're going to do is we're going to first say L is 0. And we're going to call little l, actually. And we're going to have to sort nums, but we want the indices of nums, right? So I'm going to call index equals, we'll call it index, I guess. Sorted, range, length of nums. Right, so I want all these little pointers, right? Remember the pointers I created? Key, lambda, index, nums, index. So now it's going to sort by index. So basically we're just going to get all these indices, right? We're going to start at the right, and we're going to go from range 1, because we know the first element's already in its own set, to the length of nums. Now it's in the same set until we reach the point where they're not within the boundaries, right? So we're going to say, well, if nums at index of R, right? So that's going to kind of get you from the pointer, right? So this is going to take you up that arrow and get the actual indice of the element, minus nums of index of R minus 1 is greater than your limit. Then we're in a situation where we have a new array we have to paint over. Okay, otherwise we just continue, and at the end we're going to turn rest. So now we have to paint over. So it gets a little tricky because we have to think about how this works, right? So the elements are already sorted. So we have our index and our value in zip something. And then what we're going to do is we're going to say, okay, res at this index equals this new value. Nums of value, right? Or nums of this index. Ugh. Oh, so tricky. Okay, so the indices that we're going to use are the sorted indices that we encountered in the range, right? So we'd say for sorted nums from L to R, right? And then after we're done here, we have a new place for L. So let's say L equals R. All right, and the values are also just nums from L to R because they're already pre-sorted, right? So the best way to explain this probably is by example. I'm probably explaining it to myself right now because I'm a bit confused as well, right? Because this is a bit, no. Ooh. Okay, so here, right? We look at 4, 5, 1, 0. Well, this already is the order of the sorted values, right? So if I just look at these elements and get the nums at those elements, right? What's nums at 4, 2, or 1, 2, 3, 4. And I'm just following up these chains, right? What's 4, 1, 5, 2, 1, 3, 0, 4. So those indices already are the sorted indices for the elements. So then I just need to sort the elements themselves, right, to figure out where they need to be, right? So this is the indices. These are the indices that I can use in the group, right? And these are the indices sorted of the values. So if I just set the indice to the, well, this wouldn't be, this would be indice of value. I don't know. Indice of the value, that should work. And then we just return rest. This always happens, guys. Try to do something tricky and then I fool myself. sorted LR res of I equals nums IV. That's the index. Oh, not nums, indices. Oops. Because we want the index of elements, right? Nums doesn't contain that. Nums is the normal nums. We want the indices that are already sorted, right? These indices are pre-sorted. I was looking at these values, not these values. Foolish mistake. All right. Subpar programmer. All right. So what is the time complexity of this, okay? So let's say n is the length of nums. All right, and then time, well, let's do space first, actually. For space, well, we have to create res, right? So we create this new res we're going to return. We're not like returning it in place. Now, that'd be something to see. You could probably actually do this in place. Now that I'm thinking about it, you might be able to because you... Well, no. I don't know. Because I have to create res and I also have to create this index system to keep track of where everything is, right? All the pointers. So I don't know how you would... Yeah, I don't think so. So you're going to have to use nspace already to create res. So even if you made this constant space, like doing in place heap sort or something, this is still going to take n time. And I don't know any way that you can eliminate this thing. So for space, O of n. But could be O of 1 with in place if you somehow kept track of all the order of the indexes. But it's beyond me. Maybe you know. If you know, put it in the comments. For time, well, we have to sort the array. That's going to take n log n time, right? So this is n log n. And then we look at each element. And then for each element, we look for, we look at its group. But everything's only in one group. So even though you see 2 for loops here, you might be like, oh, that's n squared. Well, really, this is looking at all the elements. But this can only look at each element at most once. So you're never going to have repeats, right? The reason why something becomes n squared is because you're looking at the same thing over and over again, right? For each element, you look at all the other elements once. Or, something that, it doesn't matter. But something that's within that, kind of asymptotic behavior. But this isn't the fact. That's not the case here, right? Because you look at all the right elements, but, this only happens for each element at most once, right? Each element is a part of most one to one group, right? So this is n, and this will run a total of n times totally, right? Not n times for each r, but in total will run n times. So this will be n, and then in here, some constant thing that'll add up to n. So it's n plus n, 2 constant operations, but they're tricky, just n. So we do n log n operations plus another n operations. So that would be n log n plus n is scaled by the n log n. All right, everybody. I hope you have a beautiful rest of your day. Bye.